Welcome to Introduction to Geology. I'm Dr. William Patterson. In this module, we're going to talk about relative age relationships between different bodies of rock. We can see Steno's idea of original horizontality and superposition illustrated in this diagram. We have a mountainous region that is undergoing weathering, producing clastic sediment that's flowing down the river. When it reaches the quiet water of an ocean basin or a lake, it's going to settle out. As it settles out, it's going to assume a nearly horizontal orientation. And what you see here are some previously existing strata that are oriented at an angle relative to the horizontal strata. We're going to get back to what this is in a few minutes. The sediment is going to be deposited as horizontal layers that are ultimately going to get compressed from the overlying weight, compacted, and converted into sedimentary rock. We can see that here using a limestone as an example from Marble Canyon, where the older sediment is beneath the younger sediment. The younger sediment, therefore, on top of the older sediment. This is known as the law of superposition. When we look at fossils, this gives us the added benefit of a higher resolution time reconstruction. Whereas sandstone that's been forming since the beginning of the formation of the Earth's crust, most of that sandstone's gone now, but it was forming then, and it would look very similar to sandstone forming today. However, there were no fossils at all in the 4.1 billion year old early sandstones compared to today. Here we have outcrop A with a sequence of rocks of different ages, and outcrop B, another sequence of rocks of different ages. We're going to start to compare these two to see if there's a relationship between any of these layers from one outcrop to another. Here we see some distinctive fossils, some fish, some brachiopods, turritellid gastropods, and ammonites. In this layer, we see the ammonite just like we do here. We see the same brachiopods and the same turritellids as we do here. So these are going to be approximately the same age. Therefore, if these fossils are found here, this sequence of rock is likely to be the same age as this sequence of rock, both of which are older than sequence 1 here. So some of these fossils found in outcrop A are going to be the same as the fossils found in outcrop B that is some distance away. Whether it's 10 kilometers or 1,000 kilometers, this can still work. Therefore, layers with the same fossils are the same age. Now here we have some additional fossils. We see the brachiopod, same species here and here, and then we add a trilobite. So when I put this together, we can see that the sequence 1 in outcrop A is distinctive. It's not found in outcrop B, so it's missing from that outcrop. Either never deposited or it was eroded away. Putting all this together, we can generate a stratigraphic section. Again, with the older rocks on the bottom, intermediate rocks in the middle, and youngest rocks on top. When we started reconstructing geologic history from the stratigraphic record, we noticed that there were sometimes gaps in the record. These are called lacuna, i.e. something that's missing. These are apparent in disconformities and angular unconformities. First example is going to be a disconformity here in time 1. We're looking at sedimentary sequences beneath the ocean. They have accumulated in layers A through D, A being the oldest, D being the youngest. Now we're going to lift this bedding up via tectonic activity. Tectonic forces cause these beds to rise above sea level, exposing them to erosion. The same thing happened to the rocks that make up the Grand Canyon with the uplift of the Colorado Plateau that also lifted nearby Monument Valley, Utah. What you see in this image are some monuments. These are all natural monuments made of Navajo Sandstone, a quartz sandstone deposited by wind during the Jurassic that has about 3% hematite present, giving it this distinctive red color. So we've lifted our rocks, we've exposed them to weathering, and erosion is going to strip away layer D. As we saw in the last image, the upper layers that have been stripped away are leaving an irregular surface of hills and valleys, just like we see in Monument Valley. In time 4, we're going to force the sequence of rocks back below sea level, and it's going to result in deposition of layer E directly on top of layer C, because layer D has been removed via erosion. The result is an unconformity. This rock is very different in age than this rock, whereas this rock may be slightly younger than this rock, and so on down through the sequence. So there's a gap, a lacuna, an unconformity here on the surface. Putting it all together, here we have deposition of a sequence within marine waters, tectonic uplift, removal of one of the layers, the D layer, leaving an eroded surface that is subsequently covered by a younger sequence of sedimentary rock. Now, in the case of an angular unconformity, we throw in an additional complication, an additional twist, literally, of the rocks. Here we have our initial sequence form. We have uplift in conjunction with folding and deformation of the sedimentary beds. So we're introducing some structure now into the previously flat-lying horizontal beds. With compression, we've crunched up these rocks. Now upon exposure, the erosion is going to strip away the tops of the folds, usually, unless they're very resistant rock, and that does happen. The result is we're left with an uneven plane with exposed portions of several folded beds. This is very common in the geologic record. Subsequently, this tectonically deformed series of beds is going to drop below sea level and reignite sedimentation on top. And as we see here, the beds are at an angle relative to one another. This is known as an angular unconformity. The angular unconformity is represented by sedimentary rock that was deposited horizontally initially. That rock was deformed, eroded, and then covered by subsequent sediment. The great angular unconformity in the Grand Canyon was first observed by the Powell expedition of 1869. And what you see here are earlier sedimentary sequences at this angle, with subsequent sequences forming in the horizontal orientation above these exposed angular beds. Then putting it all together, here we see the 1.7 billion year old Vishnu Schist. The bright Angel Shales are down here as well. Looking at it from far away, you can see the angular unconformity very clearly. So it's obvious in this situation, from this viewpoint, that this is an angular unconformity. A little island in the Hebrides of Scotland called Birsay. But it represents our previously horizontally oriented sedimentary rocks that were lithified and uplifted, distorted, and deformed such that they're now at an angle to the horizontal. If this surface is subsequently covered by the sea, which we suspect it will be due to global warming, this could be the next great angular unconformity in the geologic record of Scotland. Now, you have to be careful in that just because you see multiple angles in sedimentary sequences at different orientations, it doesn't mean that it's an angular unconformity. Again, here we have the Navajo Sandstone, and what you see here are not angular unconformities, they're cross beds. No time is missing between these beds. Beware of the cross beds. The presence of so many different angles and so many different beds here implies that there's no way this is an angular unconformity. It's just a bunch of cross beds from the crazy winds of the Jurassic Period. Another example, going up to the North Atlantic, this is from a trip I took with the National Geographic Explorer up to Svalbard, and we stopped here at Birsay, which means Bear Island. It's really in the middle of nowhere. It looks like this. In the foreground is Ian Walker, one of our Welsh scientists on the expedition, and what you see are some previously existing Ordovician sedimentary sequences that have been offset by faulting. This fault here and here is going to truncate the original sedimentary sequence. Now let's look at a complicated yet fairly common sequence of events. We're going to use the cross-sections based on field maps to understand the characteristics of the strata and the relationships between them. We have a previously horizontal sequence of sedimentary rocks that have been deformed and metamorphosed. We have an unconformity. That rock was exposed and weathered, and on top of that was deposited sandstones, limestone, shales, and eventually that was uplifted and weathered away. We end up with yet another angular unconformity here. We go from an unconformity here to an angular unconformity here. And then we have a sequence of aeolian sand dunes that become sedimentary rock, and they're going to contain terrestrial fossils. Granitic intrusions may or may not be the source of the metamorphic heat here, so the sequence of events is ordered here alphabetically. Let's form some cross-cutting relationships. So starting with deposition, time 1, we've deposited a sequence of sediment here. So we have some sand, some limestone, probably some siltstone, some shale, and another depositional layer of limestone. We're going to uplift this section, and we're going to compress it and deform it. Now, because it's uplifted and exposed, it's eroding. So we have structural deformation and an erosional surface. With the emplacement of a pluton, we're now going to inject hot material across these sedimentary layers. Because they're cutting across layers, we call this material a dike. Subsequently, this pluton solidifies, the dike solidifies, and there's some faulting that offsets the dike. So this implies the dike has to be here before the fault. Otherwise, how could the fault dislocate the dike? So these are all relative age relationships. We don't have any idea when any of these things took place. We merely know the order in which these events occurred. This brings us to the relative ages that serve as divisions of geologic time. The geologic timescale is divided into bins of time of varying lengths. These bins include eras, which are the longest periods of time, periods, and epochs or epochs, depending on where you're from. I'm from North America, so we usually say epoch. Here we see a variety of important, notable fossils. To be a really good index fossil, you should appear everywhere around the world all at once. Then you go extinct suddenly everywhere all at once. This is kind of like COVID-19. It appeared suddenly, spread quickly around the world, and then went away after a couple of years. Sort of. I mean, it's still around, and it's going to be around in some form forever, but it's not a fossil. The divisions of geologic time, therefore, are tuned to the appearance and disappearance of groups of life forms. Starting here with the Cambrian Period, we have trilobites as one of our most distinctive representative fossils. They're easily preserved because they're made of hard parts. Then we enter the Ordovician Period after the Cambrian-Ordovician Extinction. At the end of the Ordovician Period, we have one of the great mass extinctions of all time, followed by the Silurian Period. Now, the Silurian is known for eurypterids, and these grew to be about 2 meters in length. Imagine swimming through the Silurian waters with a scorpion 2 meters long chasing you. Those were the days. The Silurian Period is followed by the Devonian Period. The Devonian is characterized in this case by Dunkleosteus, a placoderm, or bone-skinned fish. This fish's head is about 5.5 feet in diameter, so almost 2 meters in diameter. It's found in the Cleveland Museum of Natural History, near where it was excavated during the building of Interstate 71. Here in the Permian Period, we have Dimetrodon, perhaps the best known of the Permian land dwellers. The Permian Period crashes to an end with the biggest mass extinction of all, known as the Great Dying. In this event, about 95% of all life went extinct at 252 million years ago. The boundary between the Permian and the Triassic is also the boundary between the Paleozoic Era, meaning ancient life, and the Mesozoic Era, meaning middle life. So we have a mass extinction at 441 million years ago, at the end of the Ordovician. We have another mass extinction in the late Devonian at 372 million years ago, and the biggest mass extinction of all at the end of the Permian, at the Permo-Triassic boundary, 252 million years ago. Starting in the Triassic, we observe the rapid evolution of dinosaurs, followed by yet another mass extinction between the Triassic and the Jurassic periods, most likely associated with the opening of the Atlantic Ocean and the outpouring of ridge basalts at the spreading center. Enormous amounts of ridge basalts. Then in the Jurassic, the big sauropods evolve. We end this Jurassic period with a smaller extinction, entering the Cretaceous period, represented here by Tyrannosaurus rex, and also known for the evolution of angiosperms, or flowering plants. Angiosperms reproduce sexually, which dramatically increases genetic variability and evolutionary rates. The Cretaceous ends violently with a bolide impact. An asteroid strikes the Earth at the Cretaceous-Paleogene Mass Extinction boundary. This used to be called the KT, or Cretaceous-Tertiary Mass Extinction, but we now call the Tertiary Period the Paleogene, and the Quaternary Period is known as the Neogene. So the Cretaceous-Paleogene Mass Extinction event killed off 50 to 65% of organisms. So it's a big one for sure, but not nearly as big as the Great Dying at the end of the Permian Period. So this Cretaceous-Paleogene extinction is enough to take us out of the Mesozoic Era of middle life and into the Cenozoic Era of modern life. In the Cenozoic, because the fossil record is much more complete, we see more fossils, and this allows us to break up these periods into epochs, smaller divisions of time or bins of time. Essentially, these are percentages of the mollusks that are present today. Just like with the geological periods, each epoch is characterized by distinctive sets of fossils. If you're still awake with me here, you've noticed that the geologic periods start and stop when certain plants and animals appear and disappear. This is not an amazing coincidence. Geologists divide relative geologic time based on fossils. When lots of different kinds of fossils no longer appear in the geologic record, that period comes to an end and the line is drawn, literally. Each and every vertical line you see here is a boundary that represents a dramatic extinction event. Starting with the Paleocene, we have few modern representative mollusks. Following the Paleocene, we enter the Eocene, which translates to dawn of the recent, again based on the percentage of mollusks that are present in the Eocene versus the present. Mammals of the Eocene include the brontotherids, also known as the titanotheres, gigantic tank-like mammals. The Eocene and the Oligocene are separated by a very interesting extinction event for which the cause was unknown until about 20 years ago. It was some work that we did on the Gulf Coast of North America using fish ear bones from conger eels that determined the extinction was caused by colder winters. I'll put a link up for those of you that are interested in reading up on that. In the Oligocene, which means few new, we have gomphotheres and hell pigs. Gomphotheres were shovel-jawed mastodons, really strange-looking animals, and hell pigs were bison-sized hoofed carnivores, not a Judas Priest or Metallica song. Fun fact about hell pigs is that some would decapitate camels and pile the thoraxes for later snacking. Following the Oligocene, we enter the Miocene, which means less recent, again referring to mollusk species. This is a time of 20-foot-long hard-headed minnows in Lake Idaho. This is followed in turn by the Pliocene, which means more recent, again referring to mollusk species. At this time, we have three-toed horses running around in Tibet that look pretty much like modern Tibetan horses. Then we enter the Pleistocene, meaning most new. Notable species in the Pleistocene include the giant beaver, Castoroides, and Homo sapiens. Next up is the Holocene, which means all recent, again referring to mollusk species. When you put this whole list of animals together in order, you have the geologic time scale. This is relative time. We know that one thing comes before or after another. We just don't know how many years have elapsed in between those events. That was as good as it was going to get until about a century ago when us isotope chemists took over. We'll get to that in the next module. Stay tuned for more information on aging when we're going to get absolute.
So take the photographs and still frames in your mind, hanging on a shelf in good health and good time. Tattoos and memories and dead skin on trial. For what it's worth, it was worth all the while. It's something unpredictable, but in the end is right. I hope you had the time of your life.